Right, so at the start of all of this, we talked about this generating the potential in sensory neurons. So the end of your sensory neuron is called a placentine corpuscle, right? And that is a mechanoreceptor, right? So it's something that's going to feel touch. So in your cell membrane, you have these sodium ion channels. They are stretch mediated because when you go and you put some pressure onto this cell membrane, it pulls them open. Inside of the membrane, it has less sodium ions on the inside than on the outside. So the outside is relatively positive in comparison to the inside. So if we go and we think about this placentine corpuscle, we can put some pressure onto it, and that causes parts of it to deform. That deformation of it goes and it causes our sodium ion channel to open up. As that sodium ion channel goes and opens up, sodium ions will go and move in. Right? Words to use, right? You can talk about diffusion. It would be better to say it diffuses down an electrochemical gradient. So, as these sodium ions go and move in, that goes and causes depolarization, right? So that causes depolarization. Because if you remember, the resting potential is minus 70 millivolts. If enough sodium ions go and move in to go and cause that to go to minus 55 millivolts, that is enough to go and generate an action potential, right, which will then go and be propagated down the rest of the neuron, right? So that is how we start off at this sensory neuron, how we start off and we go and trigger our action potential from some sort of stimulus. And the stimulus needs to be heavy enough or strong enough to actually go and cause enough sodium ions to go moving for that to go down to, well, up to minus 55 millivolts, and then that sets off the action potential, which is a little bit like chain reaction. So if we just go and move on, so the next bit that we want to go and look at is the fact that nerve cells are myelinated, right? So they are, right, they're myelinated, right? That goes and insulates them. And this myelin is produced by the Schwann cells, right? The Schwann cells go and they curl around the neuron as it's developing, right? And that insulates it. The gaps between two Schwann cells are called the nodes Ranvier, right? So a gap is a node of Ranvier. And when we go and we look at the propagation of action potentials, the action potential jumps from one node of Ranvier to the next node of Ranvier. So before we can go and talk about action potentials, we just need to go and talk about this maintenance of a resting potential. Like we've said, remember that your resting potential is minus 70 millivolts, right? The inside of our neuron is relatively less positive than outside. So outside at rest, well, you have more sodium ions than on the inside. And at rest, you have more potassium ions on the inside than the outside. So, to get us back to this resting potential, there are 1, 2, 3 different proteins or 3 different channels that we need to be aware of. We've got potassium ion channels, we've got sodium channels, or sodium ion channels, and we've got this potassium sodium ion pump. So, when we go, and after an action potential has moved down, that sodium ion channel will technically be voltage gated. So, when that goes down, right, that sodium ion channel, that shuts, so that stops sodium ions diffusing back in. Right, so now our sodium ions can't go and diffuse back in. At the same time, we've got these voltage gated, right, some of them are voltage gated, some of them aren't. Right, but for the sake of what we're talking about, we'll just talk about the voltage gated ones. Right, so the voltage gated sodium ion channels, potassium ion channels will open up. So that allows the potassium ions to go and diffuse back out to the outside of the membrane down that electrochemical gradient. So they go and diffuse out. So we're already lowering the amount of positives because we're getting rid of lots of these potassium ions from inside. At the same time, you have this sodium potassium pump that will go and pump out 3 sodiums onto the outside of the membrane for every 2 potassiums that it's pumping back in, right? So you are pumping out those sodium ions using this sodium potassium ion pump. So that is lowering the number of sodium ions inside of this membrane all the way till, actually, it's till you get to about minus 80 millivolts, right? That's called hyperpolarization. And then because the potassium ions, right, at minus 80, those potassium ion channels will go and shut again, the voltage gated ones will shut again, so the potassium stops moving out, so eventually it just rises back up to that resting potential of minus 70 millivolts. So that's basically, in a nutshell, that is how we go and we get back to that resting potential. So after our maintenance of that resting potential, we can go and start to look at action potentials. Right, action potentials all involve voltage-gated sodium ion channels and the fact that we're going to go from minus 70 millivolts all the way up to plus 40 millivolts. So it's an action potential. That is a depolarization of a particular section of the cell membrane. Right, so we start off. So further down the line, we get a change in voltage. So that change in voltage will cause these voltage-gated sodium ion channels. So that change in voltage will cause that to open up. Right? Because we've got more sodium ions on the outside than inside, that causes an influx of sodium ions into our membrane, so into the axon. That causes the depolarization, right? And eventually you'll go and you'll get enough sodium that goes and moves through. It actually goes and takes it up to about plus 40 millivolts. At plus 40 millivolts, however, the voltage-gated sodium ion channels close, right? They shut at plus 40 millivolts. So that's stopping any more sodium ions from moving in. So then after that, right, so that depolarization, that is your action potential. After that point, you go and you get the maintenance of this resting potential back. So you've got your potassium ion channels open up and allow the potassium ions to go back out. Same as, we're not going to go back to it, but your potassium sodium ion pump will go and pump the sodium back out, and it will take it back down to a resting potential of minus 80 millivolts. Right, that minus 80 millivolts is called hyperpolarization. Right, that hyperpolarization ensures that a nerve impulse, or an action potential even, only travels in one direction. Because at minus 80 millivolts, there is absolutely no chance that those sodium ion channels behind where your action potential has moved on, it ensures that they cannot open again until they get back down to resting potential. And the whole thing goes and kicks off again. So that hyperpolarization, the reason for it is to ensure that your action potential only travels in one direction. And then it just carries on, it moves down. Right, remember, that's your salutary conduction and your propagation of your action potential moving down all the way down your axon length until this end it would eventually reach a synapse. Remember, your action potential moving down, if it's myelinated, so if it's got Schwann cells, it jumps from node to node rather than having to go down the entire length, because that means that your action potential moves a lot faster. Right, so unmyelinated, it moves at about 2 meters per second. Myelinated, it moves at about 200 meters per second. So it is considerably faster.